Welcome to Monochemistry. Today we're going to look at the gas laws. Gas laws are from Chapter 5 in the AP Chemistry textbook. And what I've done here is I've outlined all of the different laws. But before we talk about each one, I'm going to talk about ideal gas behavior. So this sheet is available on my Moodle site, so you don't have to copy it down per se, but you should definitely write down any questions you might have about any of these things as we go through so that you get a better understanding of it. And you should certainly take notes on each of the individual laws as we go through as well, because this is the information that I've given you on the Moodle site. Okay, so first of all, there are 4 different laws that led us to the combined or the ideal gas law equations, which are these ones right here. And I'm going to, before we get into each of the laws, I'm going to just define or explain a little bit about gases. So in chemistry, in physics, whatever you want to call it, we have the kinetic molecular theory. And essentially, you've been learning about the kinetic molecular theory since you were in elementary school, probably. If you've been talking about the fact that there's such a thing as atoms, and that atoms can be in a state of matter of solid, liquid, and gases, and how the particles are very dense in solids, less dense in liquids, and completely separated in gases, you've talked about the kinetic molecular theory before. However, there's another branch of the kinetic molecular theory that specifically deals with gases, and that's what we're going to focus on today. So first of all of these laws are based on what we call ideal gas behavior. And there's 4 different aspects of that. Number 1, gas molecules are spread apart. We already talked about that. Individual molecules are said to have a mass, but a very small and therefore negligible volume. Number 2, gases are in constant motion. Collisions between particles are elastic. In other words, when they hit each other, there is no gain or loss of should say loss, not lose. No gain or loss of energy between them. Number 3, there are no attractive and repulsive forces between the particles in a gas. And remember, this is ideal gas behavior. It's not necessarily true for every gas. Number 4, the average kinetic energy of gas molecules is proportional to the kinetic energy. Should say temperature. Any 2 gases at the same temperature have the same, so this should say not kinetic energy, should say temperature. Okay, so it's proportional to the temperature. Any 2 gases at the same temperature have the same average kinetic energy. Okay, so let's talk a little bit about it. I'm going to go through them in this order here. Let's talk a little bit about the gas laws and see if we can make some sense of them. Okay, so the first one is Boyle's law. And Boyle is the oldest of the 4 people who came up with their laws. And basically, he examined what would happen if you changed the pressure, what would happen to the volume of a gas. And he kept the amount of gas and the temperature of the gas constant while he did this. All right, so basically what he noticed, quite simply, was as he increased the pressure, the volume decreased. So they were, in essence, inversely proportional. So if we had this, we said pressure is going to be inversely proportional to volume. Okay, so this means proportional. It's a symbol that means proportional. And then, of course, if you were to calculate the constant, or the slope of that line, then it would be pressure is equal to some sort of constant divided by the volume. Okay? Now, over time, he realized that constant, no matter what gas he was talking about, assuming the mass and temperature were the same, was the same for any gas, and was the same across the board. So what he developed was an equation that looks something like this. P1V1 is equal to P2V2. And that is what we call Boyle's law. Charles's law, again very similarly, was at constant mass and pressure, what happens to the volume as the temperature is changed. So as the temperature increases, what he found was that the volume of the gas increased. So they were directly proportional. Okay, so the volume of a gas was directly proportional to T, or, if you prefer, the volume of a gas was equal to some constant times T. And he used that information to come up with his law, which looks as follows. V1 over T1 is equal to V2 over T2. Okay? And despite the fact that Charles looks a little bit inebriated, I think anyway, and he lived in France, so he probably had access to lots of wine. He did a lot of work in this area, and his law has proven to be true over the years. Let's move on to the next one. All right, so Guy Lussac, I'm trying to use my French here, Guy Lussac, he was French as well, came up with a law that dealt more with the temperature. And basically it was at constant volume and constant mass of the gas. And what he found was as the temperature increased, the pressure increased. As the temperature increased, the pressure increased. So what we're looking at here in this picture, imagine that this is your container. Okay, we have it at a particular volume, and we have a certain amount. Pretend, even though it doesn't look quite the same, that over in this one here, we have the same amount of gas. The volume is definitely the same, but what's going to happen as I increase the temperature from T to 3T is that the pressure in this side, this container, is going to increase. So what he would have written would have been something like this. P1 over T1 is going to be equal to P2 over T2. Okay, because, as I've said before, the pressure and temperature, the pressure is going to be proportional to the temperature. As you increase the temperature, the pressure will also increase. And so pressure would be equal to some constant times T, and so he came up with this equation. Okay? Let's check out the last one, going from nerd to even nerdier. We've already seen a picture of Avogadro, but as you can see, it never gets easier to look at that face. I don't know why. All right, so Avogadro's law dealt with constant volume and constant temperature, and essentially it said that the pressure of a gas was proportional to the number of moles of a gas. Or the pressure of a gas was, equal to some constant times the moles. Okay, so as the concentration of a gas increases, so we start off with this, low concentration, fewer collisions. As the concentration increases, so does the collisions, and therefore so does the pressure. So his law would look something like this. I'm just trying to squeeze it up here. P1 N1 is going to be equal to P2 over, N2. Okay, so those are the laws, and what those laws allowed us to do was to come up with the combined gas law, okay, which is essentially this: P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Okay, now at constant anything, you can eliminate some of those. Okay, so at constant anything, you can eliminate some of those values. So in other words, if the moles are constant, you can cross them out of that big equation. All right, so that in a nutshell are the different laws And they, of course, allowed us to come up with the combined gas law as well as the ideal gas law. And remember, these laws apply to gases at ideal conditions, not non-ideal conditions. We'll talk about those a little bit later on. Here are the resources, the places I found the pictures and animations for this video.